Alrighty. Well, I hope everyone enjoyed the orangutan while you were waiting. I'm going to get started. I don't see anyone hopping on Zoom. I think a lot of people are probably just working on their term projects, which is fine. So we're going to get to it and just talk about Markov decision processes. This will probably, just because we didn't have any catch up, or like canceled classes really, or anything that put us far behind. We will probably make this the last week of new content. So last formal meeting. And then over the next couple weeks, you can study and work on your term projects. So if we look at the syllabus, you can see that you have the term project and presentation recordings are due on the 18th. So you've only got a couple weeks to do that. And then the term project reviews are due the week after, meaning that you have to have done your own term project and presentation recording. And then by the 25th, you have to have reviewed the your peers. So some of your one or two of your peers. I think it was I required 2, but let me double check. We'll double check. Make sure I'm not lying to you. I think it's under discussions, right? Yeah, term project. Okay. So reply to at least one of your peers. Okay, so you only have to do at least one of your peers. I would recommend, just enjoying the process, learning, because when someone dedicates several weeks to a particular topic, the general thing is that the majority of people in the course have probably dedicated at least, I would say, a couple, 3-4 weeks, hopefully to some sort of project. So it could be a review, or it could be actual implementation of some sort, and a report on that. So I would say that these are perfect opportunities to take someone's hard work, and they basically are summarizing and showing you how they went about doing something, and that gives you a great opportunity to see how different projects and different techniques were used, and maybe make you aware of certain topics that you might not have been aware of, or maybe give you a deeper understanding in a particular area of artificial intelligence. So I'm looking forward to looking at the videos and watching videos and looking at the presentations as well. So pretty much a few people have asked me a couple questions here and there about the term projects, but it seems like everyone's, I hope, on the way to producing something pretty solid. So I think we should be good on that. All right, so yeah, that's the plan. I don't know that we're going to have class next week or the following weeks. These 2 weeks are when you're literally getting your stuff due. So I think next week is just going to be project work. So you can just spend the week working on your projects. And then this week is the Markov decision processes. So I'm not, I haven't done anything official, but there may be a small homework on this. I haven't quite decided yet. It kind of depends on feedback I get and just how much work everyone's putting into the term projects, if I get kind of a sense of that. But if I do anything, it would be pretty short. All right, so Markov decision processes. So first off, there are what we could consider simple decision models, and then there are more complex decision models. So simple decision models often, any of these, we're often concerned with optimization. So suppose we must make a decision, and we have different approaches to choose from. We want to determine the desired outcome and behave in a way that leads to that result. Okay, so this leaves open the question of whether it is always possible to achieve the desired outcome. Okay, list the courses of action that are available and determine the outcome of each of them. And then one of the outcomes is preferred because it will have the one that maximizes something of value. So for example, amount of money received. So this does tend to intersect with, and it's obvious for those that are familiar with game theory that this does definitely involve game theory, and this will have a massive impact on reinforcement learning and how some robots learn and a bunch of other techniques related to that. So, but this is optimization theory, operations research, and game theory are all a big part of this. So finding the maximum or minimum, or maxima and minima, of something is a familiar procedure in basic calculus. So suppose we are interested in finding the maximum of a function f of x. We can differentiate f and set the result to 0. And that is when you find that you have a solution to the equation. Okay, that would give us, to that equation, that would give us one or more values of x at which a maximum is attained. Sorry, that is spelled wrong. Attained. All right, so making decisions. So the simplest case for decision making is when there is no randomness in the environment. So once a choice is made, the outcome is certain. So no random environment, everything's very, very static. A choice of behavior in a single decision problem is called an action. So let us call the set of alternative actions A, and this could be discrete. So it could be, for example, a set of actions that are explicitly listed. It could be infinite, or it could be finite, but it could be discrete actions. So A sub 1, A sub 2, etc. Or it could be continuous. So unit interval between 0 and 1, for example. A payoff is a function p. In this case, we'll use p for payoff, but typically we would maybe use a different symbol because p usually means probability, and we will actually find probability later on. But just in this context, know that it means the payoff function. So this function p, pi would also be another alternative, I suppose. So p maps actions onto real numbers that associate the numerical value with every action A that is a member of the set A. So an action A opt is an optimal action if the payoff of A opt is greater than all other payoffs that are possible, greater than or equal to, so no less than any other payoff, which is the action that optimizes the payoff P of A. So that's what A opt is. Okay, a little example of optimization. So a job seeker is offered two jobs, J sub I, or J sub 1 and J sub 2. Their possible actions are A sub I equals accept J sub I, with I being in the set 1 or 2. So they're going to be picking one of the two jobs. Oops. They're going to pick one of the two jobs. And the payoffs are the salaries. So J1 pays 85,000, J2 pays 87,000. Thus, the payoff of A1 is 85,000 and the payoff of A2 is 87,000. So of these two, this is very simple, obviously, but therefore the optimal strategy in this case, because there's nothing else going on, we would say that the payoff of A opt is by taking action A2. So we end up that the optimal A opt is A2. So note that the optimal decisions are not altered if the payoffs are given in UK pounds or euros or Chinese yuan, or nor if 1,000 is added to each payoff. So if you change it linearly or perform what we call a collinear transformation, that is called an affine transformation. So these alterations that do not affect the overall outcome here, but they just change the have kind of a linear effect on the system and don't really change the outcome, are called affine transformations. Collinearity, again, as a reminder, it means points on the same line initially are still on the same line after some sort of transformation. So you haven't bent it into a quadratic or done something logistic or logarithmically to it. As defined previously, an affine transformation is a transformation that preserves collinearity. It changes payoffs P of A into payoffs P prime of A, according to the rule P prime of A equals some alpha times P of A plus beta. where these are constants independent of A and alpha greater than 0. So some fundamental concepts just to kind of review some of the stuff we've probably mentioned throughout the course, and you've probably heard before, but just to make sure that everyone can kind of get their bearings with the simple decision processes. And if you've done any kind of game theory, you're probably familiar with a lot of this. But probability theory describes what an agent should believe based on evidence. Utility theory describes what an agent wants. So we're talking about what is the utility of say a game or a situation or whatever. That ends up being what are the payoffs for different actions. So utility theory has to do with what does the agent want. Probability is what the agent should do based on evidence. And then decision theory puts those two together to describe what the agent should do overall. So our probability says what the agent should believe based on evidence, and utility is what the agent wants. And then you actually put it into action with decision theory. So based on what the agent wants and what the probabilities or the evidence suggest, what should the agent do to achieve its goal? So that should have a question mark at the end. Sorry about that. Rational agents. Continuing, we have decision theory. Can be used to build a system that makes decisions. These decisions are based on considering all possible actions. The system chooses the one that leads to the best expected outcome. And a system that has these properties is known as a rational agent. Utility theory shows that an agent whose preferences between lotteries, are consistent with a set of simple axioms. The agent can be described as possessing a utility function. Furthermore, the agent selects actions as if maximizing its expected utility. In this context, utility would refer to the value or benefit from participation in a game or simulation. And by game, we don't mean, haha, that's fun, or, playing Black Ops or, Halo or Prison Architect. We're not talking about something that's necessarily fun. Game theory in the game theory context could apply to actual video games or board games, but it's anything that could have cooperative or adversarial behaviors in it. So simple decision processes. So these are the processes that go with the simple decision model. So simple decision processes, combining beliefs and desires under its uncertainty. So an agent, like all agents, has to make a decision. So it has available actions A, so certain actions A, and there may be uncertainty about the current state. So we assume, now here's where we start kind of reusing P, which is kind of bad. I should have changed it to pi in the last slides probably, but we assume the agent assigns a probability P of S to each possible current state S. There may be uncertainty about the action outcomes. The transition model is given by P probability of S prime given S and A, which means that if you are currently in state S and you take action A, what is the probability that you end up in state S prime, which could be the same state as S, but it's just means basically this is the transition function. This ends up being the transition function. We will see this a little bit related to Markov processes as well. So abbreviated, this is the probability of the result of a, this is a different way of saying this whole thing over here. The result of A, so given an action, particular action, and you're in a current state, it's kind of implied. Then what's the probability of that happening and getting you to a state S prime? The two are related as follows. So basically the P of result of A equals S prime is equal to the sum over all S of P of S times the conditional probability P of S prime given S comma A. So decision theory in its simplest form deals with choosing. It should be choosing. Looks like I'm going to have to update the slide or upload the new slides. Deals with choosing among actions based on the desirability of the immediate outcomes. That is, the environment is assumed to be episodic. Okay, so the agent's preferences are captured by a utility function. U of S is the utility function, and this assigns a single number to express the desirability of the state. So it assigns a scalar value typically to express whether this state is desirable or not. We also have concepts of expected and maximum utility, or expected and maximum expected utility. So the expected utility of an action given the evidence, so we'll call it EU of A, that's the expected utility, is just the average utility value of the outcomes weighted by the probability that the outcome occurs. All right. Now, this right here, again, this is not a union symbol. This is the utility function. You multiply by this probability right here. So the maximum expected utility, MEU, says that a rational agent should choose the action that maximizes the agent's expected utility. So the action should be the maximum of all those possibilities for each state of that has the highest expected utility. So argmax are the elements of the domain of some function at which the function values are maximized. Decision trees are also used when you have to make any kind of decision, but especially with simple decisions, we often use decision trees. So decision tree is a representation of a function that maps a vector of attribute values to a single output value of the decision. Okay, so you have all these attribute values, and you want to map it to a single value, which is the one that you're interested in. That's the output. That's the decision you make. So the decision tree starts at the root and performs a sequence of tests following the appropriate branch until a leaf is reached. Okay, example with decision trees. So here's a nickel and dime scenario. This is a story. A man hears that his young daughter always takes a nickel when an adult relative offers her a choice between a nickel and a dime. Now, you'll note that this whole thing may seem kind of weird, but sometimes, especially when there are young kids involved, at least at certain family reunions I've been in, when there's a really young kid involved, sometimes the family will get a kick out of the fact that the child will look and see that the nickel is bigger, so they think that it is worth more. I had a situation happen with some friends of the family. It was a very young kid. He was probably 4, I assume, maybe 3 or 4. And he was in some sort of like, I'm assuming it was Cub Scouts or something like that, where he had to raise money. And I thought I was being generous by offering to buy the whole box. So what I did was I gave him a large bill and took the smaller bills that were in the box so that I could essentially get change out of it, and then bought the rest of the box. Well, he started freaking out and crying and screaming. He thought I was taking his money because there were more bills that ended up in my possession. I gave him one of them. So he was counting the number of bills rather than the value of each bill. So I ended up just letting him. I ended up letting him keep the bills he had already, plus the large bill that I gave him. So it was one of the most probably expensive boxes of chocolates I've ever bought from a Cub Scout, but it ended up making him not cry. So that was worth it, I suppose. So anyway, this is a common thing that we know about kids. They generally they look at quantity of things. They don't look at the value of each individual thing. So this is kind of a cutesy little thing people will pull on kids because they think a nickel's worth more than a dime because it's bigger. So a man hears that his young daughter always takes the nickel when an adult relative offers instead of the dime. He explains to the daughter a dime is twice as valuable as a nickel, so you should always choose the dime. But she replies, now in this scenario, it does seem that she's actually aware that the dime is worth more, but she's kind of messing with people and trying to make sure she gets as much as possible. She says, Daddy, but then people won't offer me any more money. The idea is that if she takes the dime at the beginning, then they won't try to offer her any more money because there's no cuteness involved. It's like, oh, she didn't fall for it and take the nickel, so I guess she just keeps the dime. So she thinks if she keeps accepting the nickel, She'll eventually accept a dime, maybe, but maybe she'll keep getting nickels when offered between dimes. So ultimately, she will actually end up making more money. So the story is an example of a decision process. A sequence of decisions is made, although the process may terminate before all potential decisions have been taken. But this story illustrates two components of strategic behavior. So first, immediate rewards are foregone in the expectation of a larger payoff in the future, and second, the behavior of others is taken into account. So that's foundational in game theory, and we specifically are describing it in terms of strategic behavior. Strategic as we're looking long term. Okay, here is the decision tree of the situation. So she knows that she'll at least be able to get out, maybe 2 rounds with the relatives. So if she picks the dime immediately, it's not cute anymore. So they just keep the dime and haha, everyone had fun. But if she takes the nickel, someone else or the same person might offer her a dime and a nickel again, and expecting her to pick the nickel again. But this time she picks the dime. So what happened in this scenario is she's actually, instead of getting 10 cents, if she did not forego this exciting, more expensive valued thing here, if she went down the nickel route, then took the dime, she'd actually end up with more money. All right, so a decision tree is representation of the function that maps this vector of attributes again to the decision. Oh, you know what? I think that's got to be a repeated slide. I think that was maybe for emphasis, but I'm going to remove it. All right. So now we're on making complex decisions, Markov decision processes. I guess since we're in the area already, I'm going to upload this slide to replace the one that's currently there. And if we have more corrections, I'll do that. So often, like that one, often we are concerned with decision making in a stochastic environment. So now we're talking about more complex situations. We're dealing with what we would maybe call probabilistic scenarios instead of a deterministic scenario. So stochastic will refer to situations having a random probability distribution or pattern. These situations are typically much harder to predict with precision because with a deterministic case, you know, if you do this, this will happen, and if you do that, that will happen. It's deterministic, right? So previously, we were concerned with one-shot or episodic decision problems, where the utility or payoff or value of each action's outcome was known a priori to the scenario. So you know if you take this particular set of actions, you're going to get a particular payoff. So if you know it a priori, then you know exactly what you need to do, pretty much. But now we're going to concern ourselves with sequential decision problems. An agent's utility depends on the sequence of decisions rather than individual decision. So these problems incorporate utilities, uncertainty, and sensing. I like the Oxford comma, so I'm going to put that in there because why not? All right. Special cases of these problems include search and planning problems. That's not right. One second. Okay. So Markov chains. So this is the first part of the Markovian discussion here. We have Markov chains in the early 20th century. So we've got 1900s. Andrei Markov in Russia studied stochastic processes without memory called Markov chains. Okay, so stochastic or probabilistic processes, random probabilistic processes without memory, so they don't remember, where they've been essentially, called Markov chains. So such a process has a fixed number of states. The process randomly evolves from one state to another at each step. And by randomly, we don't necessarily mean that it's just like completely out of the blue. In this case, we're using the probabilistic notion that it has a certain probability of transitioning from one state to another. So the probability for it to evolve from a state S to a state S prime is fixed. So that probability is fixed and only depends on past states. Um, So whatever state got you to this current state is what's affecting it. We don't have to look at the whole history and then decide in context what we do next. We just decide on the current state we're in. So that's why we say that the system has no memory. Okay, there's an example of a Markov chain. In this case, making a particular move here. Suppose there's a process S0, that's the start state. That would mean that there is in this particular diagram, a 70% chance that it remains in that start state at the next step. So when you go to make a particular move, it chooses to go back here with 70%. Eventually, it's bound to leave the state and never come back. So notice there's no incoming arrows from anywhere. So once it leaves, it will not come back. So with a 20% chance, it will go to S1. With a 10% chance, it goes to S3. If it goes to S1, then it will likely go to state S2 with 90% probability on the next round. And then it goes to, then it comes back to state S2 with 100% probability. That's why that's a 1 there. So it's definitely going to go back. It can't stay or anything else. It just comes back. And it may alternate many times, but eventually it will fall into this kind of terminal or black hole state right here. This has, once you get into this S3, whether it was from the very beginning or whether you get there from S1, this S3 acts as a sink and it just stays there. So basically you have 100% probability once you get here, you stay here forever. So Markov chains have very different dynamics. They're heavily used in chemistry, thermodynamics, statistics, robotics, and many other areas. Now, built on this is the concept of Markov decision processes, which were actually proposed by Richard Bellman in the 1950s. So this is a couple decades down the road. Richard Bellman, you may recognize his name, probably more so you may have heard of the Bellman-Ford algorithm, for short as PAS, which is slower than Dijkstra's algorithm, but it's capable of handling negative edge weights. So it's a little more flexible in some scenarios. But Richard Bellman's also the inventor, essentially, dynamic programming. So it's an entire paradigm of programming. You may have been taught in an algorithms or data structures and algorithms, or just algorithms, advanced algorithms course, whatever. And dynamic programming, and he also made other contributions in biomathematics and other areas of mathematics. If you recall, the dynamic programming is a paradigm. It has some similarities, or at least is reminiscent of divide and conquer, but divide and conquer, you go from the top down, whereas dynamic programming, you try to remember previous things you've done, so it makes it easier. So for example, Fibonacci sequence is notoriously bad to try to calculate with divide and conquer. So if you start at the top, you end up doing like, f of 5 is going to be f of 4 plus f of 2, or f of 3, right? And then add that f of 4 turns into f of 3 and f of 2. The f of 3 turns into 2 and 1. The 3 turns into 2 and 1. The 2 turns into 1 and 0. So it keeps on going, and you do a lot of repetitive calculations of things that you've already calculated in other areas. So dynamic programming would say, why don't we start at the bottom and start with the, Fibonacci sub 0, Fibonacci sub 1, and go our way up. And then we can remember where we've been before and don't have to recalculate. We just keep it in some sort of an array, some sort of data structure, dynamic array, linked list, whatever, and look at it later. And that's what you do. So really, really good contribution. So Markov decision processes, they resemble Markov chains. However, at each step, an agent can choose one of several possible actions. Additionally, the transition probabilities depend on the chosen action. So in the other one, you're just kind of floating around with a certain probability, but the actions here that you're choosing can determine probabilities. Okay, so moreover, some state transitions return some reward, positive or negative. So that should click in your brain that we've got reward system here. We've got a reward system here with Markov chains. So this should give you an example or give you an idea that this is going to have some impact on reinforcement learning. Okay, so again, these are similar to Markov chains. Again, Markov chains just kind of flow with a particular probability, and you usually end up in some sort of sink like this, or frequently do. And then Markov decision processes are similar to Markov chains, but at each step, the agent can choose several actions, one of several actions, and these probabilities depend on the chosen action. Moreover, some state transitions return a reward, which could be positive or negative. It says reward, so that tends to give the impression that it's something good. But in this case, it is not necessarily. It could be negative. It could be a punishment, but we still call it a reward. It's whatever you get after taking a certain action. So the agent's goal is to find a policy that will maximize the reward over time. So in this context, a policy includes the actions that should be taken given current states. Basically, you could set up a table and say, if I'm in this state, I should try to take this action. Okay. And the optimal policy is the policy that maximizes the reward. And clearly, this is used heavily in reinforcement learning. So here's the situation. We'll look at this over the next several slides, but you can kind of get an idea here. There are different actions here in the triangles or diamonds, and there are different states in the circles and different rewards on the edges here, as well as probabilities. So here's an example. Again, you have the S sub i's, S sub 0, 1, and 2. Those are the three states in this particular Markov decision process. It also has up to 3 discrete actions, the A sub k's, for each one of these. So you have the S sub 0 has A sub 1, A sub 2, A sub 0. S sub 1 has A sub 0, A sub 2. And then S sub 2 has just A sub 1. So up to 3, because this one has 3. So as an example, if we look at this, if we start in S0, the agent can choose between actions A0, A1, and A2. So A0 would go this way down here. A1 goes up, A2 goes this way. If the agent chooses A1, it remains in this state. So this goes, this is a loop. This is 100% probability because of this action. There's 100% probability that you end up back in state S sub 0, and there's no reward on this edge. If you choose action A sub 0, there's a 70% chance of gaining a reward of plus 10. So that's what that 0.7 means. You could get a plus 10 reward here. And you could get you could go into action A2. That would be the other possibility. You'd have 80% chance of coming back or 20% chance of moving forward to state S1. It could try again and again to keep getting this 10, but at one point, or at some point, I should say some point, it's going to end up in S1. So at some point, the probabilities are just not going to be in your favor. You're either going to get a 30% from down here if you keep picking it this way. So that might be a good plan for a while. But eventually, even if you pick A sub 0, instead of it taking you back here, it will take you over here. So this is probabilistic, right? So the probability if you pick action 1 again is 100% you're going to end up in a loop. The probability that you will end up back in a loop but also get a reward if you pick A sub 0 is 70%. So that seems a little bit more desirable maybe. And then you have the 30% chance that you're going to go, if you pick action A sub 0, you're going to have a 30% chance of going to S sub 1. Okay, so in state S sub 1, there are 2 possible actions. So there's only 2 possible actions. You have A sub 0 and A sub 2. So A sub 0, A sub 2. And it's 100% probability, if you pick action A sub 0, that you would end up back in S sub 1. But if you pick A sub 2, we have a little bit of a problem here. It looks like there's a pretty big damage here, or a negative reward or a bad reward. So walking through fire is bad. 100% chance you're going to walk through fire and end up in S sub 2 and have negative 50 here. And then here, if you pick A sub 1, you could end up back at S sub 1, or you could end up with an 80% chance to S sub 0, or a 10% chance of S sub 2. Okay. So in state S sub 2, there's no other choice to take than A sub 1, because there's only one outgoing arrow. So it can either loop back here with no reward, or go back to S1 with no reward, or have a huge payoff with plus 40 over here. But the problem is, with that 10% here, you could also end up back in S1 and have to go through the fire again and get negative 50. So there's always, that. It's a 10% chance, but it still could happen, of course, with 10% probability. So can you guess which strategy will gain the most reward over time? Well, in state S sub 0, it's clear that the action in state S sub 0, it's clear that the action A sub 0 is the best, because A sub 1 is not going to do anything for you, period. A sub 0, if I pick that, there's a 30% probability I go to S sub 1, but just looking at that doesn't hurt me. But there's a 70% chance that I could get a reward. So that's actually quite desirable. Oops. In S sub 2, if you look at that one, the agent has no choice but to take action A sub 1. So there's really no option. And then in S sub 1, you have two options. You could take A sub 0 or A sub 2. It's not obvious whether the agent should stay put or go through the fire. So you could just stay there for eternity, or go through the fire and try to get more reward. Bellman found a way to estimate the optimal state value of any state S, called V star S. That's the sum of all the discounted future rewards the agent can expect on average after it reaches state S, assuming it acts optimally. So here we go, the Bellman optimality equation. So Bellman showed that if the agent acts optimally, then the Bellman optimality equation applies. So you can see that there is a recursive behavior to this, right? So you see gamma multiplied by this recursion right here. This recursive equation says that if the agent acts optimally, then the optimal value of the current state is equal to the reward it will get on average after taking one optimal action plus the expected optimal value of all the possible next states that the action can lead to. So all the possible values of the next states. In the equation, just to review some of this here, the T of SAS prime is the transition probability from state S to state S prime, given that the agent chose to go A. Okay. So I might, for example, with S sub 0, I might choose action A0, and I'm hoping to get this loop here to go to S sub 0. But there is a probability I will go off into S sub 1. So that's not as desirable as just, sitting here and making a lot of money, or points or what have you. So given some sort of diagram like this, and I give you a transition function, so S sub 2, A sub 1, S sub 0, this says if I'm in state 2 and I take action A sub 1, what's the probability that I get to S sub 0? So we can look at this and we see it's 0.8. Now, if I said, what's the probability, or if I do transition of S sub 2, A sub 1, S sub 1, then you would say it's 0.1, because it's 10%. We also have the concept or notion of this reward here. So the reward, if you're in a current state, you took a current action, going to another state, or it could be the same state, but going to a state S prime, it's the reward that the agent gets when it goes from state S to S prime given that the agent chose action A. So in this case, if I say I'm in S2 and I choose A1 and I want to know what's the reward if I go to S sub 0, if I get to S sub 0 because of the probabilities, and that tells me that I will get 40 points to go back there. And then we have this gamma, which is a discount factor. Building on top of the Bellman optimality equation is this value iteration algorithm. It's essentially the same thing, but we're just saying that we are turning the equation essentially into an algorithm. So we're saying that it leads directly to an algorithm that can precisely estimate the optimal state value of every possible state. So you first initialize all state value estimates to 0. And then what you would do is you would iteratively update them using this value iteration algorithm. So that's this equation up here. So an interesting result is given enough time, these estimates are guaranteed to converge to the optimal state values corresponding to the optimal policy. So note that V sub k of S, at any point v sub k of S, is the estimated value of state S at the kth iteration of the algorithm. And this algorithm is actually an example of dynamic programming. So you may recall this means a problem is broken down into easier subproblems and attacks them iteratively from the bottom up. Okay, instead of top down, which would be a divide and conquer. So you're going bottom up right here. It's bottom up. We can see that actually because if we have a current v sub k and we get a v sub k plus 1, we can tell that we're moving up instead of starting up here or making a v sub k based on a v sub k plus 1, so something lower. Okay, now here is our kind of our demonstrative example. This is explained not as well as I would hope in the Russell and Norvig book on AI, but so I kind of extended it and made it a little bit, hopefully a little bit better. So consider the graph where we want to get from the start to the goal state plus 1. So now, your possible moves or actions rather that you can choose in any state, you can choose up, down, left, right. The -1 is I'll get to that if you're near a wall in just a second, but you can choose up, down, left, right, wherever you are. The -1 right here is a bad state. We don't want to do that. And then in this particular case, this black cell right here is just a wall. We can't go in there. So you select an action at a time. The set of actions is up, down, left, right. If the direction is into a wall or goes off the grid, then you stay in the current place that you are for that turn. So let's say I'm at start and I'm asked, where do I want to go? Then let's say I choose left. So it's going to point me to the left here. Then I would say if it does in fact give me the outcome left, this would not take me off the grid. It would actually keep me in this start state. If this was deterministic, this whole problem would be very easy, pretty much trivial. You could just say up, up, right, 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 and then you'd be in the goal state, right? So that's kind of what we want to do. That would be a perfect plan if we got our way, but we're not in a deterministic environment. We're in a stochastic environment. So stochastic, again, means there's a probability. So this is our little direction, intended directions and where we actually end up. So whatever direction we choose, we're going to go in that direction with an 80% chance. Okay. Now, the general idea is that actions are unreliable. You can have the environment can throw things at you that you weren't expecting, and you end up, like you may want to get to a particular place on the road, but then it ends up there's construction. You have to go around. 10% chance that there's an accident or whatever. However you want to view it. In this particular case, you pick a direction, but you could end up going, or the action that actually gets executed could end up at a 90-degree angle with the action that you picked. So it could end up going, if you choose up, it could actually have a 10% of executing to the left, which in this case would take you back to start, or it could actually go to the right, which would take you to the right, okay? But notice that if I'm in start and I pick left as my action, you have to picture this thing rotated. So if I pick left as my action, the 90-degree things would be up or down in this case because I'm picking left. So in this particular situation, I do have a 10% chance of bumping into the wall down here, so that would keep me at start, or I have a 10% chance of going this way, and it would actually move my character up. So the environment won't always go along with the deterministic solution, the one that you want, as the actions are unreliable. So there could be something going on that prevents you from getting to where you need to be or where you want to be, which is your utility. So we have the following components to our Markov decision process. So here's the components. We're going to look at them more carefully. We have states, S. So you can think casually about, well, what would a state constitute in here? And the state would really be like, what cell are you in, right? So I would say, I mean, we could go by zeros, but let's say this is cell 1, 1. And then let's say the rows increase going up and then the columns increase going right. So you have 1, 1, and you want to go up to 2, 1 or 3, 1. And then this is the second column over here. So this will be row 1, column 2. That's 1, 2, etc. So the goal state is in row 2, column 4. So 2, 4 is where our goal state is. So the model, also called the transition function, this arrow here is basically, if you think in a programmatic point of view, this is actually giving you a return value. So the transition function, or the model, says we are in a current state. We pick an action, and we are this is the particular state that the second state, or the state that we're gunning towards. What's the probability that we end up in a particular state given that we are in a current state currently and we're taking a particular action? Okay. And then we have, of course, the actions. Sometimes it's useful to look at it in terms of a function, and sometimes we just look at it as a set of possible things we can do. And the thing that makes the Markov decision properties, one of the things that makes the Markov decision properties unique, is also that we have rewards. Okay. So these are 3 different ways of looking at it. R of S, this is usually the most common. R of S and A, R of S, A, S. These end up being equivalent, which we'll look at in a second. But this is basically telling us we get a particular reward for being in a particular state. Additionally, the definition of the Markovian property is that only the present matters. So we're not considering a full history. Our transition function only depends on the current state. That's what the present means, in light of the actions being taken. And the rules don't change over time. So the rules, or we could say the physics of the environment, or the environment itself, is stationary. Okay. That does not mean that our individual component or thing that we're moving, our entity we're moving around the map, is stationary. It does not stay in the same state. But the rules themselves don't change in a Markovian situation. So little more thorough description here. So states and actions. So these are parts of the Markov decision processes. So where we are in the world, the grid position is the state. So since there are 12, there are actually 12 states in this example. We would say that 11 of them are reachable. This black one is not, because we're looking at that as a wall, so we cannot actually go into the wall. But we could say that the start state is at, that's wrong too. That would be, no, that's right. That's row 3, column 4 is the goal state. So 3, 4 is the upper right corner. Damage is 2, 4. So this is 1, 2, and then 1, 2, 3, 4. Okay. And then we have actions A. So this is the set of actions. We've got a set of states, which is all 12 of these things. We could say 11 are actually reachable. And then we have actions, things you can do while in a particular state. Now we can always pick up, down, left, right. And notice in this particular scenario, there's no action to not move. But sometimes when you take an action, for example, such as left, if I say I want to go left from the start position, if I get that 80%, it does trigger at 80%, then I will actually stay in that start state. Or it's possible if I say, hey, I want to go up from the start state, given this set of probabilities here, the direction I pick as the action, I have an 80% chance, but there is a 10% chance I will still stay in the start state, because I will actually, the actual output of the system will tell me that I'm going to go left. But once it says that, it says, hey, you're against the grid here, so you can't go left, so just stay where you are. And then there's a 10% chance I would go right, okay, even though I picked up. So we tend to view the actions as a function of state, so it's often written as A of S, but there could be some actions that are valid in some states and not others, etc. But usually we just consider it a set of actions. But in some states, the action just has no effect. So instead of saying, let's consider it reduced actions in each state, we assume we have those actions up, down, left, right in all states. But if we pick a state and the probability turns out that we don't move that particular direction and keep in the same state, it just essentially is having no effect. Okay, so again, going back a little bit, we have states, we have actions. I skipped over the model because that's a little more complicated and involves actions. And now we're going to go back to the model and then talk about reward and eventually policy. So here's the transition function, or the model. Okay, so now we know that you have locations you can be in, right? States. And then we also know things that you can do in the world. Those are called actions while in a particular state. So you have states and actions. And now we have this transition model given certain states and actions. So basically, this is describing the rules of the game you're playing, the physics of the world. Now, we're referring to this as a game, but this is game in the sense of it could be an actual game, but it is game in the sense of like game theory. Okay, so it could be adversarial, cooperative. It could be you versus the environment. It's just it's a model of a system or simulation of you making progress towards a particular goal state. Okay. In that sense, a reinforcement learning model, which uses MDP a lot, is playing a game in that sense. So the input to the transition function are S, A, and S prime, and then the output, or the return value, if we're thinking from a programming point of view, is the probability that we will end up, even though we are in state S and picked an action. Remember, we're not guaranteed we're going to end up in this S prime here, or any particular S prime, but the probability that we end up in a given S prime, given that we were in state S and chose action A. Okay, so the input to this transition function are the current state, action to take, and the state you will transition to, or that you are considering transitioning to. The output, or return value, again, is this probability that you end up in S prime given the current state. Note the probability summed up over all the potential S primes in a given state must add up to 1. Okay, so for example, this is a perfect example here. This is our driving force in this particular diagram, but this one could be different for each cell. It's possible. Like it could be the start state has, if you pick a direction, it's 80%, 10, 10 at 90-degree angles. But there could be another cell, maybe you're over here, and it's a 90%, 5%, 5%. Or if you pick this action, there's a 90% you actually go to the left. I mean, it could be any of those. You'll notice with this particular model, you don't go backwards. That's not one of the, you don't have a probability of going backwards. Unless you, like if you pick a direction, you won't go at a parallel or opposite direction. Okay. So if this were deterministic instead of stochastic, we could still use a Markov decision process to model it, but we would just have the intended state with 100%. So you would not have these perpendicular arrows here, and you'd just have an arrow going forward with 1.0. So that means no matter what I do, I would go in that direction. So again, with this particular game or state, or set of states, this simulation, the deterministic process is actually fairly trivial. because you would just say up, up, right, right, right. And that's how you get to your goal. And that may be your plan, even with the Markov decision process. But remember, in this case, if I want to go up, up, right, 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 I may pick up, but then I have a 10% chance I'll go to the right. So what do I do now? Okay. So now I have to decide, what do I do from here? Do I go back, try to go back, or do I go this way? But when I go this way, it's getting me closer to the -1 too. So do I want to try to go around it? Do I want to go up? What do I do? Okay. And again, reminder that the Markovian property states that only the present matters. We're not concerned with the history of states taken. We are using our transition function, which only depends on the current state. So that's the present. And then the rules don't change over time. So the rules of the quote physics of my environment do not change over time. Okay. So it might seem weird that we wouldn't consider previous states or history when selecting the next state. In that case, you'd need a list of state information. So I could do something like this. I would have these S sub Ks or S sub Is rather, from 1 to K. I'd have a series of states. I could consolidate them into this representing the state, but that wouldn't be Markovian. Mathematicians, you would think, would be irritated with not being able to use historical information, and even historians would get ticked off as well, because history repeats yourself if you don't consider it. But mathematicians will typically be satisfied with these Markov decision processes because we can essentially convert any non-Markovian process into a Markovian process by bundling the historical information into a single current state. Because remember, we have to have a single current state right here. With the Markovian situation, we have to have the single state, but we could make that state information more complex than just where are we located. But typically we're just concerned with that. We're just concerned where on the board are we located. That's definitely what we're doing here. The reward is the next topic up here. And this is the one where it should start smelling a lot more like a type of machine learning that we talked to very early on in the course. We talked about supervised, we talked about unsupervised, and we talked briefly about reinforcement learning. So supervised is when you have things that are labeled. So we can think of it as giving them X and Y coordinates or values, because you have an X, and we're saying that if you have certain input X, you're going to get an output Y. With the reward scenario, we can actually look at it as ultimately having 3 different things we're considering, because we have a state we're in, we have an action, and we have an S prime. So what's the reward of that, given that? So it's kind of like XYZ. So the reward is something you get for being in a particular state. For example, if these are dollars, we would say you get $1 for making it to the green square. You get $1 taken away if you're going to the red square. The reward encompasses our domain knowledge, tells you useful information, or the usefulness rather of entering into a particular state. So other helpful notions of reward, although these are all functionally equivalent, the R of S is the most common we'll look at, and but these might give you an idea or let you think differently. So R of S sub S comma A would be the reward for being in a state and taking a particular action, or you could think of it as reward for being in a state, taking an action, and ending up in another state. Okay, so these are just more, maybe giving us more details. So these 4 things define what a Markov decision process problem is: state, model, actions, and reward. Okay, so that defines the problem. What is an MDP problem that we can solve? It tells us we have states, models, actions, rewards, probably states. But we also want a solution. Okay, we're not just interested in just where we are and what actions we're taking. We want to also know what should we do, okay, in light of different states that we're in. So the solution is actually to a Markov decision problem of Markov decision processes is called a policy. It is a function that takes in a state and returns an action that you should take. Okay, so pi of S, this is the policy, given that you're in state S, you should take this action. Okay, so a special policy, pi star, is the optimal policy, which maximizes your long-term expected reward. And you can see, you can view reinforcement learning like this as, I don't know why that is down there like that, but that's weird. Okay, so you can view reinforcement learning as similar to supervised learning in that respect. So how do we capture our desire to end up in a goal state plus one green states as part of the policy? The policy tells us if you're in a state, you should take an action. Okay, so mappings for the states and actions would be something like this. So for example, if you're in the start state, your action that you want to take is go up. Okay, because we are trying to go around, not go around this way because that brings us closer to the red state. So we want to go up and then over this way. If you're in 2-1, so row 2, column 1, so this state right here above the start, then you want to go up again. If you're in 3-1, so again, row 3, column 1, then you would want to go to the right, etc. Okay. If you're in 1-2, I guess they did this, you'll say you want to go to the right there. In general, we would say that the policy, given you're in state S sub I, you want to take action A sub K. You always know what state you're in with a Markov decision process and what action to take due to the policy. So you may start with a plan to go up, up, right, right, right. So that we would not say is part of the policy. We're just saying that's part of our plan. Up, up, right, right, right. Okay. But the policy only affects what are you currently in and what do you do next? Okay. So the policy does not encompass the overall plan. Because of the nature of the stochastic nature, the stochastic nature of Markov decision processes, at each step, you might not end up in the state you intended because of this thing right here. Again, this tells me if I want to go up, I do have an 80% chance that I will go up, but there's a 10% chance it will tell me to go to the left, which I'll bump into the wall over here and then stay, or it'll give me a 10% chance I'll actually maneuver to the right, even though I wanted to go up. So then I have to consider, oh, well, I'm here now, what do I do? Okay, do I go right again, which takes me actually closer to the red as well, or do I try to go back to the start? Okay, you could actually tell it, hey, go bump into the wall, but then eventually you would go with 10% chance either back to the start or over here, right? So that may not be a good plan. Okay, the policy will tell you based on the current state, where do you go? So policy question. As an interesting note, now this is really cool if you think about it. So let's say somehow, because of probably, even though you intended to go up, up, right, 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 because of the different probabilities here, you just got really super unlucky or lucky, however you want to look at it, and you ended up in this cell right here. So it's row 2, if I'm increasing the row numbers going up, because our start's down here, and then the column numbers increase, go to the right. So I'm going, I'm in column 2, or I'm sorry, row 2, column 1, 2, 3. So I'm in 2, 3 where our smiley face is here. What action might you want to take? Now, it might seem very reasonable to pick up because that would get us closer to our goal state with an 80% probability. But why might you not want to do that? In other words, this is our little hint here. Why might you choose to go to the left? In other words, you kind of rotate this sucker and try to go to the left here. Why might you want to do that? Anyone want to take a guess? Is there any reason, instead of saying I want to go up, I want to instead point to the left or try to go to the left? Even though I know I can't actually go there because there's a wall there, given the context of this thing. Anyone have a good guess? You can raise your hand on the toggle if you want to, or I'll just answer it. If you're all sleeping, it's possible. Okay, so you might want to go to the left here because if you look at this thing, you have an 80% chance of the action being executed. Hey, actually go in that direction, but I can't because it'll bump me back. It'll bump me back each time, so I'm not losing anything. I'm not getting damaged. And because I'm aimed in that direction to the left, and there's no probability of going in reverse, I will not hit the -1, that's for sure, because there's a 0% probability of that. But there is a 10% probability I would end up going down because I'm aiming to the left. If you think of this thing rotated 90 degrees to the counterclockwise, I have an 80% chance of going here, which keeps me in the same place. But I have because of this one right here, I have a 10% chance of actually going down and then a 10% chance of going up. So it may be desirable if time is not of the essence, or if you're not being like clocked with a certain number of turns and don't have very many left, then it might be more desirable to aim at this wall here and then hope that the 10% executes, that when I get out of this kind of like crashing into the wall situation, I end up going up. If I end up going down, then okay, well, I have to pick another thing to do. What do I do? Okay, so going up seems more direct, but if you're avoiding the red square, consider wasting a few turns maybe, and then hope that you end up going to the right, or you possibly end up at the left, but you hope you're going to go to the right. I say the right because if you say I want to originally go to the left and I'm pointing at this square right here, if I've got this rotated, then this is now your right. But I'll just say going up on the grid. So you have this 10% chance that you're going to go up, and you might get closer to this, and then it's real clear, hey, I just want to go to the right then and go into the green square. But I'm trying to avoid this -1 here, okay? So I have that pi over 2 angle that I'm going in. So we can view reinforcement learning as similar to supervised learning. Supervised learning takes labels of elements, so X, Y, to make predictions. So for example, the state action pairs X, Y, S, A, you learn policy pi to link the two. But reinforcement learning can be thought of as taking kind of X, Y, Z, because you have kind of a state action reward situation. In this scenario, you try to find the optimal actions for the policy pi prime based on the rewards given states and actions. So you have more stuff to consider here. And that's kind of how reinforcement learning works, is you're actually considering not just where am I now, where am I trying to get to, but you're also considering reward along the way. So I might get a bigger reward maybe going in a direction I wasn't initially considering, and maybe it's even away from the ultimate goal state by 1 cell or something. Maybe it's worth it. Okay, so that adds a completely new situation into the mix. Okay, so here's some really good references. I would recommend them very much. Obviously, the kind of the epitome Bible of AI, the modern approach, artificial intelligence by Russell and Norvig from 2021. Machine Learning by Stephen Marsland again. He's the guy, and I think he's in Australia. I think he's in Australia or New Zealand. I think it's Australia. Hands-on Machine Learning by Aurélien Guéron. This one actually ended up having a pretty decent short section on MDPs and Markov chains, so that was actually kind of a surprising fact that it even had the topic. And then there's Game Theory, Decisions, Interactions, and Evolution by James N. Webb from 2007. All right, are there any questions? Otherwise, I will end the Zoom meeting and then upload the recording once it's processed. So we did end up getting a few students. I have a chat. Okay, no one. Okay, you don't have a question. Anyone else have a question? Any questions? Okay, if there's no questions, this ended up being kind of short. I apologize for kind of the last minute, let's do it on Zoom situation, but I know there are only a few people that show up anyway when you do show up. So I figured it wouldn't be too big of a deal. My cat sounds like a ridiculous dog ate my homework situation, but my cat is really ill. So I am kind of sticking around and might end up taking him into the vet. So one of my cats, I have 6 currently, which is kind of scary, but I'm the crazy cat person of my town. The other thing, just if you came in late, just as a note and just to kind of follow up, is Next week, we're not going to meet because I want you to be able to take the time to work on your projects. So we're not going to have a new topic next week, but do be on the lookout. I haven't decided yet, so don't freak out. It would be very, very short just to have a third homework assignment, but it would be like insanely short and probably involve MDPs. I might say, here are your transition functions. Here's your current state. Here's your action. Tell me, or here's your current state action. What's the probability you end up in such and such state, or something like that. So it wouldn't be anything too insane if I do assign it. But do focus on your term projects and presentations because those are worth a very big portion of your grade. And again, as a reminder, so no, we're not meeting next week, Zoom or otherwise. You can obviously email me, ask me things on Discord. It doesn't matter. I will try to help. And then on the week of the 18th, term projects and presentation recordings are due that week. And then the week after that, after you've already turned in your project and presentation, the reviewing, you have to do a review of at least one of your peers. So you have to watch one of their videos and look at the presentation and say what you liked, blah, 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 or what you thought or what you learned, or it doesn't have to be really long, just something, hey, I really thought this was insightful. I really liked da, 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 da. I learned this, I learned that. Whatever you want to do as far as that's concerned. Probably something better than, hi, that was great. I would do something a little more extensive than that, but the term project reviews are due that week. It is a non-trivial part of your grade, so definitely do those too, or you'll be kind of sad. So these are the most important, but then the following week, you have to have your reviews up. All righty. Okay, let me see here. I'm going to end the recording right now.